I'll be talking about uniting math and music, evaluating various tuning systems. First, I want to talk about the inspiration for this paper. My whole family is very artistic, and I'm not. My dad's been in theater his whole life. My sister's studying theater right now. My mom's a piano teacher, and over the last couple of years, she's been teaching herself how to tune pianos. And while she's been doing that, she's been teaching me a lot about the music theory behind it. And I became very interested in it just in the mathematical relationships that are behind all the different ways you can tune a piano. And so that's why I decided to write my paper about this. Okay, so most people see the relationship between math and music. Most people understand that there is something that defines the way music works. And that we all know that physical and mathematical definitions define, like frequencies and whatnot. What most people don't know is how structural all of music really is. That no matter what you look at music, you can find mathematical structure all the way from the way you set up chords to the way you tune the piano. So some different ways that you can handle this are the modern ways that something called temperament. And what that is that that's how all modern pianos are tuned. It's a thing called equal temperament. It's that all notes are equally defined apart from each other. Now this may seem like a basic idea to us that all notes are the same distance apart. That's only an idea that's about 200 years old. Before that, no one ever did it that way. Before that, there were so much for tuning systems that people all over the world fought about, killed each other over. And so what I'm doing with this paper is I'm looking at all the major ancient Western tuning systems and then comparing them to the modern systems. Some major work that brought about the modern tuning system is from Sir Isaac Newton. He made a connection between music and light, connecting sound and the EM spectrum, which everyone knows now just from the basic trigonometric connections between the two. But he pioneered that connection, and from him, the door was open to the modern way of defining music. My work mimics the work of Stuart Isaacoff and David Wright, who both wrote books on the subject, Temperament and Mathematics and Music. Two very good books coming at it from both sides of it, Temperament from the musical theory side, and Mathematics and Music from the math side. So I started off with their work. So just some basic music theory to get us started. Back in ancient history, music started being formed into a 7-note vocal scale. And we all know that as the do-re-mi, probably from Sound of Music or something like that. Those names actually come from a poem about St. John, which is pretty cool. A modern 12-note tone scale is you take the same thing and you just add in the sharps and flats. And each one of these, if you repeat them, you get octaves. And repeating them over and over again, you begin to be able to form equivalence classes using these different notes. The distance between, on a 12 tone scale, between A sharp is called a half step. And then between A and a B, or Do and a Re, and stuff like that, is a whole step. Now some things that become very important when you get to tuning is how different sounds come together. And 2 sounds at a time is diatonic, 3 is tritonic, and so on. And these are only important when you get to multiple notes sung together. So for the longest time, there weren't multiple note instruments. And so it didn't matter. But once those became prevalent, the tuning systems really began to matter. And how they started off doing it was using cardinal ratios, using the numbers 1 through 6, and making ratios between the notes, like 6 to 5, 5 to 4, stuff like that. In modern day, we use cents, which is a logarithmic unit. Every half step is 100 cents. And I'll get to that later to find what a cent actually is. And what all these are trying to do is increase consonance, which is when 2 sounds sound good together. Now, the golden ratios or cardinal ratios always make consonant sounds. They always sound good together. The problem is when you use different kinds of ratios together, you start to get bad sounding things, which are dissonance. And what we have in modern times is equal temperament, which flattens out everything and tries to make everything sound good together. So a little bit more about the history of everything. Pythagoras started all this way back in the day in ancient Greece with a machine called the monochord, which you see here, which was 2 fulcrums and then a weight off the end. And what he would do is he would put another fulcrum in the middle to change the length of 2 halves of the string. And he was able to discover the ratios that, say you had one length that was twice the length of another, those were an octave apart. If you had it 3 to 2, that was a major fifth apart. That sort of thing. And so from that, he was developed his golden ratios about what sounded good together. The numbers 1 through 6, like I said earlier, form these ratios. And from the first two, 1 to 2, which is an octave, and 3 to 2, which is a fifth, he formed Pythagorean tuning, which was the major tuning system all the way up into the 1500s in Western music. But this began to be a problem, like I was saying earlier, when the widespread use of fixed string instruments came about, when the multiple tones played together really began to matter. This especially became a problem with the development of the piano. And so what happened was people began to experiment with different key layouts. And you see here, this has a lot more keys on it than our modern day piano has. And what they were doing is that for each possible note, you could get a lot of different ratios, which we'll talk about some more later. And that came about with a new kind of tuning called just tone tuning. But then later on, when this obviously wasn't going to work, the idea of temperament came about, which tempering is flattening all these ratios to equal each other. Because you can multiply ratios together and they'll be off by just small fractions. And so what temperament does is it squishes them together. And the difference between those are called commas. And that came about the mean tone tuning system. And then finally, Newton came up with the connection to the EM spectrum. He assigned each note a color and was able to show how that connection went further and further into how music works. And he actually came up with a logarithmic expression that is our modern day definition of all the notes. Okay, so some basic principles involved. We have Hooke's law here, which defines the tension in a string, and then how it vibrates. Then how it vibrates uses this constant here to define what frequency is going to vibrate at. This is the definition of free vibration in a string. And then the connection between that vibration and the frequency you hear. Some other important principles that are involved are beating, which my little graphic stopped working. I don't know if you all saw it earlier. When you have two frequencies that are very close together, they form a third frequency called the beat frequency. And what that is that you'll hear the amplitude of the two frequencies rising and falling in a constant pattern, and that's your beat frequency. The importance of this is that in like a piano, when you have beat frequencies, every even numbered beat frequency will cause another note on the piano to sound. Like say you have two notes on the high scale and you play them together, the beat frequency from those two will sound whatever the natural harmonic of a low string is. And so the beating, which was not evident to people back in the day for the tuning system, becomes very important in evaluating the modern day stuff. Okay. So the very first tuning system I'm going to talk about is Pythagorean tuning, which uses the golden ratios 1/2 and 2/3 to define all the notes. Now if you apply it first to the do re mi scale, you start off with a do, which I assigned to A440, and then you move up a fifth, which is going to be so right here, and you multiply this frequency by your ratio, 3/2. So you see we have 440 times 3/2, okay? Now, to form the rest of the scale, you keep going around in order, adding 4, effectively modulo 7 every time. So you see, for your next one, it's going to be re, and you raise your ratio to the next power. So you see, your first one is 3/2 to the first, and then you go another 4, and you get 3/2 to the second, another 4, 3/2 to the third, and so on. And what you do is you just keep doing this until you form all the notes. You see, I've gone through and done it twice just because I wanted to see if the pattern continued and what kind of error you would get as you go along. And on this one, you can see the error right here is a constant 6.78%. But when you move on to a full 12-note scale, it begins to change. You see the right here, I just have the exponents, so you can see along each one. And oh, sorry, I forgot to mention. What you do to get backwards is between the octaves, you divide by 2. Go back. I'm sorry, I forgot to mention that earlier. So once you found the note way down here, you just divide by 2 enough times to get back to your original scale. So anyway, going back to the 12-note scale, you do that, and you begin to get some wildly different error numbers. They begin to change quite a lot. And so what I was trying to do is I was trying to find the structure involved in what is making this. I was able to develop this equation, which is basically you take your 3/2 relationship here and here, and then your 1/2 for octaves, and you just both raise them to powers. So we have this one, and this one. And those are this table here. I'm able to find the actual function for it, but this is just the one-to-one for each one. So A is your base frequency, alpha is your base frequency. And then N is the number of half steps you want to move up the scale. So you can move up a total of 12 half steps to get there. And so this equation defines this chart. And so I wanted to evaluate this to see how accurate it was. Comparing it to accepted frequencies, if you base everything off of your first go around of the chart, you have very low difference between accepted frequencies. Your second one's a little more, third a little more. Eventually, if you move all the way up to going around the circle 5 times before you go and find the rest of your notes, you're getting a pretty vast difference. Now this is in hertz, and this is number of half steps away. But this is a little bit misleading because once you get up here, your frequencies are already in the thousands, so that difference isn't quite as big. So if you normalize it, it becomes pretty constant. And you see this is just from the cyclic nature of this equation here. That's what these peaks and troughs are for. But you can see that if you go around that cycle once, then you get an error of about 1%, and it keeps going up. And so how they would form a scale back then was that you're able to get your octave on either side from this first row, an octave on either side of that from your second row, and on up. So a constructed set of frequencies, here's our modern day accepted, and this is what they would have been able to get using the Pythagorean tune. And you can see from the error that here's your middle octave with A440 there, and then your octave on either side, octave on either side. So you can see that when you're close to whatever you start at, you're pretty accurate, within 1%. But the further you get down the piano, or whatever instrument you're using, the more and more you're off. So that when you're down here, your notes are actually 1 or 2 notes off what they're actually supposed to be. So, for something that came up for in ancient Greece, it lasted pretty good all the way up until the 1500s. Once they started moving to pianos, they moved into trying to use other ratios to define how they got to the other notes, and that is called just tone tuning. And that's using all the other cardinal ratios to define them, define the notes in it. The idea came up with by a monk in the 2nd century, but it didn't become prominent until pianos were used and other multi-string instruments at the end of the Renaissance. And what it does is it's based off of Pythagorean's golden ratios, 1 to 2, 3 to 2, and so on. And basically what you do is you start off with the do, as we did before, and you define your 2 major ones, your 5th and your octave, like we did last time. And then what you do is use the other ratios to keep going. So you define your 5th, your 3rd and your 4th, which give you mi and fa. Then what do you do to get the rest of them after you've used all your cardinal ratios? What they did was they started basing off the other ones off of other notes they'd already found. So moving from other notes, you're able to fill in the rest of the scale. Now this was an interesting idea, but the problem was you have lots of different ways to get there. And so when you're using on the simple 7-note scale, the errors are pretty small. But when you move up to a 12-note scale, you begin to get a lot more problems. You can set up all your ratios, and you're only able to get a few of the notes. And then to find the rest, what do? You try and connect them other ways. But there are lots of different ratios that can get you to all the other notes. And so if you use this combination with this one to get here, you're going to get a different ultimate fraction from what you get going this path. And so a couple of them, the first time you do this, all stayed about the same. But a couple of them already have 3 different possible fractions you can get just after one go around of it. And you can see the error is pretty small on this first set. But they begin to get pretty big when you go further into it. And this is pretty hard to see just pointers, so I decided to do it graphically. It's a lot easier to see if you do it graphically. So what we have here is just, instead of using notes, just a generic placeholder, we have our original note, minor 3rd, major 3rd, 4th, 5th, and octave. And so what I did was basically, you take whatever color it is, and that's what you multiply by first. And then you drop down, so for this one, you would start off with your lower 5th, and then you multiply by each of the other ones to get the note above it. Does that make sense? Sort of. And so you can see here, you get a lot of different possible combinations for this one note. If you go down the line, you have two different possible fraction combinations just here alone, and they repeat in a lot of places. But just in the first level of moving one note and then another note, you have lots of different possible fraction combinations. And if you do it one more time, it begins to get really grossly, hugely big, which is horrible to try and calculate. And so for this first one, I was able to write myself a nice little program that would pop out what the fractions ended up being and then eliminate the duplicates, because a lot of them duplicate. But you can see that using this tuning system, you have a number that equals 1 that doesn't equal 1. And a lot of places where you have multiple notes that just repeat. And so if you use it just to define the notes around it, it works really well. But if you try and expand it out at all, then the system breaks down completely. And so this was the tuning system, this was the reason for having multiple piano keys right on top of each other, so they could try and use all these different fractions together. Because they thought each one of them was useful. Like, if all these ratios are good, then we ought to be able to use each of these notes in this spot. But they sounded different. And so they were just playing different notes at the same time for whatever they thought was necessary. When this stopped working, they came to mean tone increment, which is basically taking all those bad gaps and flattening them. Now you can do this either off of Pythagorean or just tone, it works either way. What you do is you take whatever you end up defining everything as and just multiplying it by proportionality constant. And for the Pythagorean, it follows a set pattern, so I decided to follow with that one because just tone's just gross and I didn't want to follow that out any further. And this little adjustment factor is called a comma. And what this particular one does is all 1/4 comma. It reduces the error to 1/4% off of all of the Pythagorean notes. And so here's that added function off of the Pythagorean, which is all just a bunch of constants. I'm sure these have rational values as fractions, but I didn't have time to find those, so I just left them as decimals because that was good enough. And if you compare the error, you can see here's the Pythagorean, and then here's your constant, 0.25% of an error. Now the problem with this is that your ear can hear 0.25% off. Your ear is very delicate. You can hear all the way down to 0.1% error, which is a problem with why this stuff doesn't work, which is a problem of why eventually they had to move to the current system we have, which is equal temperament. Newton came up with it. Well, not Newton himself. He came up with the fundamental equations that musical theorists came to. And this is the base equation for it, where you have a reference frequency as before, and then however many notes you have in your scale, like for us it's 12, goes in your radical, and then however many half steps away from your base note you want to move is up here. So say you start at A440, that's your 49th note in the piano, so your two numbers here, N naught and alpha would be 440 and 49. And to get any other note in the piano, you just put in how many half steps, whatever note number it is in the scale, like 1 for the lowest note, 88 for the highest, and you're able to get your frequency. And this is our modern Western accepted notes, and you can see the definition of a cent is 2 to the 1 over 1200 times whatever your first frequency is. So each half step in our scale is 1 cent, 100 cents apart. And this is how modern piano tuners tune their piano, is by trying to get, you're able to calculate the cents off with some sort of hearing device that'll sometimes tell you how many cents are off, or it'll tell you how much you need to move it, that sort of thing. But that should say cents, not steps. Sorry about that. So that's where this number comes about. There are 12 steps, and so if they want the octave divided even into 12 spots, it's going to be 1,200 cents. But this modern system still has some problems. If you compare it, if you play just a pure cardinal ratio from Pythagorean and compare it to the same set of notes from equal temperament, you can hear the difference and hear that the pure cardinal sounds better. The beating that comes from those sounds good, the difference of the frequencies, and you can hear that difference when you compare them. Now, most of us wouldn't know that that's a problem because we've grown up in the modern Western musical world. I mean, we grow up hearing the notes the way that equal temperament says they ought to be. But if you heard them differently, like my mom was showing me when she was tuning the piano, you could hear the difference, and it doesn't sound the same after. So some problems that equal temperament has is it doesn't account for symphony ringing, which is the beat frequencies that cause other notes to sound. That's what symphony ringing is. And if you play chords, they try to slip into these ratios. Like you'll hear the frequencies modulate just a little bit, trying to fit into it. And so it changes the beat frequencies and stuff like that. And also each time you tune a piano, you have to tune it based on the temperature, where it is, the humidity, that sort of thing. So there are a whole lot of factors that the equal temperament equation doesn't take into account. And a lot of music theorists believe that there is a master equation. It doesn't need a bass reference frequency or anything, that you can just plug in stuff and it will give you what the actual frequencies are. And another problem with the equal temperament is that this definition is just an approximation. Like I said, he has to use a reference frequency. It's not just the definition of how far they have to be apart. But then again, that's because it's a logarithmic scale and it can't be the same each time. So a lot of people are trying to solve that with modern alternate tuning systems, which most of them try to modulate things just a little bit, but all of them fall into just tone, where they have all these different notes, and they're trying just to account for them with different frequencies. And so like you can add all these modifiers to the equations I've been showing you all you want, but they still just slip into this kind of same pattern. And so most of the modern research that's being done on modifying the current equations aren't solving the problem correctly, I would say. They're just trying to flex out of the modern ones and go back to what they used to have before, and they're not working. So some conclusions I've drawn from this is that the modern equal temperament tuning is the best we have, and it sounds the best, and it works the best. But it doesn't fully define all the parameters involved, and it doesn't take into account the way strings ring together when you play them together. It doesn't take into account what setting the piano's in, that sort of thing. It's just a generic equation for generic setting. And some other things that it doesn't take into account is the significance of the golden ratios that all the notes try to slip into when you play them together. Some people say the master equation doesn't exist. It may just be one of those things like Maxwell's equations where they're good, but there are so many little parameters that affect it in whatever area you're in that you can't totally define it. It has to be defined for each instance, that sort of thing. So, any questions?
So someone has perfect pitch, that's a learned thing from what they've been used to hearing.
Mm-hmm.
Did you also get into the thing, I don't know if you've noticed that when they play the bells, you know, and those are digital, but they're designed so that when a bell actually rings, it's going to have overtones.
Mm-hmm.
So if you play a C, an E, and a G bell together, the overtones don't match.
Mm-hmm. A lot of that has to do with Hooke's law.
Yeah.
The material itself will generate other harmonics. Because each, a string, it's easy, the harmonics are just half and whatnot. But bells and stuff like that, the harmonics aren't exactly perfect ratios with each other. I think that might have something to do with it. But yeah, again, the overtones don't match because it's trying to make those golden ratios. And when you use an accepted note, those don't make the same ratio.
Any other questions?